Good morning. This is Tim Stewart. I'm president at Visual Decisions, and we're here today to talk about improving delivery with Industry 4.0 and operational excellence. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements such as 30% increases in OEE, 50% scrap reductions, and much more. But Industry 4.0 alone won't automatically make the business better. The culture of the organization and the business processes have to be adapted to take advantage of the new capabilities in order to drive real improvements. So that kind of spoils the thunder, but in terms of why add Industry 4.0 solutions to lean practices, the first question is, what do I mean when I say Industry 4.0? And the people on the call might already have their impression. I'm utilizing this graphic from the World Economic Forum with the very, very small print. But over on the left side, I've pulled out some things from there that are critical to the conversation for today. And in particular, I'll be focusing on advanced analytics, IoT, machine learning and AI, and augmented reality. And those technologies are absolutely wonderful, but they don't do the job on their own. Great example of this is a Fitbit. A Fitbit is a wonderful IoT device. I've been wearing one for 8 years now, and it does exactly what it's supposed to do. It collects the raw data from the sensors on the device. It pushes that information up into the cloud. It utilizes machine learning to take those raw signals, turn those into steps and heartbeats and activities and so forth. And yet, even though it does exactly what it's supposed to do, I still haven't lost weight in those 8 years that I've been wearing it. And it's not the fault of the Fitbit. The Fitbit, again, does what it should. But I haven't changed my behaviors. And because I haven't changed my behaviors, I haven't lost the weight. And in order to make those changes, you have to actually do something differently tomorrow than you do today that utilizes that technology. And it's the same thing in manufacturing. So what we really focus on is combining the smart factory with the lean factory that already has a lot of those improvement tools built into it. So how do we combine the capabilities of these smart solutions with the existing process improvement tools that we have with lean manufacturing or operational excellence? And is it worth it in the first place? And this is the result of a study done by Bain back in 2019, where if we compare the savings from traditional lean standalone to what you can do with the combination of digital and lean, you can see that there's a lot more that can be done when you combine those two things. So very quickly, our approach to this is, from when we start engaging with customers, if they already have a complete vision, that's fantastic. We work from that roadmap. If not, then we work with them to create, what is that roadmap? What is the art of the possible? How can we let the business case kind of drive where we go with it and so forth? And once that map is in place, then what we try to do is to create the shortest path to get from where you are today to where you want to be. And very often that includes leveraging existing investments that you already have. So what is the data that you're already collecting? How can you feed that into your continuous improvement process and take advantage of that and so forth? And then filling in the capability gaps, whether that's with technologies like IoT or AR or anything else, and then integrating across different processes. The example that I use here all the time is looking at warranty data. You don't want to look at just the warranty data in isolation. You want to look at it in the context of what was happening on the shop floor when those products were made, the design process, et cetera. But throughout it all, you have to keep in mind, what are the process changes that you have to put in place? What are the training? What is the training that you have to do for your people and so forth in order to really take advantage of those things? So when we look at kind of the nuts and bolts of how to combine Lean and Industry 4.0, one of the things that we see is that manufacturing has done a great job pretty much throughout history of embracing a lot of new technologies, whether it's robots or cobots or lasers or anything that seemed futuristic 20, 25 years ago. You see that in almost all manufacturing operations these days. Continuous improvement we're still doing on whiteboards and pasting pieces of paper up on there, and manual data collection and standing next to a line with a clipboard and a stopwatch. And so there's a lot of room for improvement in terms of embracing technology within continuous improvement. So I've done a number of different webinars that go into a lot of detail on how to actually transform operational excellence, looking at the management system itself, the MOS, the visual controls, how you manage standard work in this process, down to how you make Gemba more effective and so forth. And then the Lean toolkit itself in terms of how you do root cause analysis, how you do value stream mapping, FMEAs, et cetera. And I'll give a couple of highlights here today, but I encourage you to either go to my website at visualdecisions.com to look at some of the other videos that I have on this, or just reach out to me at tim@visualdecisions.com. And I'm happy to go into a lot more depth in how to do this mapping and how to transform OpEx. So if we look at a typical Kaizen process, certainly there's room to utilize data more effectively in how we identify the problems, how we prioritize where we're going to do the Kaizen, instead of just whatever machine went down last or whoever's shouting the loudest. Analyzing the current process, doing that root cause analysis, creating different solutions. The solution space is so much bigger when you have some of these different technologies that you can utilize for error proofing, et cetera. Testing those out, measuring the results, standardizing the solution, being able to kind of encode that new process makes it something that is kind of hardened within the organization that way. And there's pros and cons of that, but if you harden it in a yet flexible way, then you get the benefits of both sides. Looking at a root cause analysis framework, whether you're doing something as simple as who, what, when, where, how, 5 whys, going through a fishbone diagram, doing graphical evaluation or FMEAs, or more of a Six Sigma approach using analysis of variance, design of experiments, et cetera. Having data and detailed data and contextualized data is absolutely critical to being able to do those analysis effectively. And again, I don't want to get too much into the details in this particular webinar, but there's a lot of concern from a Lean perspective in maintaining fingerprints on the process. How do you still drive the ownership of the Lean process while you do automation in that process as well. And for me, it's all about the standard work. So instead of having the standard work be actually walking over to the whiteboard, recording things, then walking back to your station, how do you take the automated data collection and now do something with it? So you still put standard work in place. You still expect people to interact with and understand that data. But instead of that being the end of it, now you actually expect them to take actions based on what they're seeing. And that can deepen the understanding and actually drive more ownership than simply writing things down. All right, so let's talk about throughput. When we think about throughput, one of the primary measurements of that is OEE when we're looking at individual processes. and kind of the aggregate OEE, or overall equipment effectiveness, looks at throughput for the entire facility or department or whatever it might be. And we can break that down into availability, performance, and quality. I did quality a few weeks ago. So I'm going to talk about availability and performance today. I'm going to spend a lot more time on availability, but I will touch on performance as well. When we look at resource availability and how that impacts throughput and so forth, certainly the one that gets the most attention is machine breakdowns and maintenance. And I'm going to spend some time going through that today. But I'm going to go actually more in detail on that topic next week. Then, some of the other things that we can look at are, setups and changeovers. How do we, minimize those? How do we, utilize some of the Industry 4.0 techniques and combine that with a SMED analysis and so forth? If we look at different process failures or manpower issues, material issues, all of those can impact whether or not we're actually producing things in our process. So starting with the maintenance, if we look at different maintenance practices, we have autonomous maintenance, having the operators do things, preventive maintenance, condition-based, predictive, and then kind of associated practices, looking at Kaizens and being able to run an improvement event to make sure that we eliminate one source of downtime, doing an FMEA to identify what are all the different failure modes and the effects of those, and then putting plans in place, running Kaizens to either mitigate or eliminate those different failure modes. So when we look at autonomous maintenance, things that are helpful for the operators in that space are automatically tracking the counts. So if the oil needs refreshing or replacing every, I don't know, however many days or weeks or pieces produced or anything along those lines, by automatically tracking when that is done, when it's due next, and proactively notifying the operators that that task is due to be done, it's something that we can make certain that it's getting performed when it should be. Optimizing that maintenance schedule. So instead of doing it every X number of pieces or every X number of days, we can actually look at the condition and help this become more of a condition-based activity as opposed to a time-based or piece-based activity. And then running a full optimization on that so that we really understand what are the driving factors, what do we need to look at and take action upon, are things that we can absolutely put in place with Industry 4.0 tools. And then notifications, having that easy task list each day, giving them the prompt to take the action, making it highly visual for instructions. You can even do augmented reality based instructions so that they can very clearly see what needs to be done. And you can provide support for different operators in that process to make things happen and so forth, so that if a task is due but your primary operator isn't there, it can still get done. Automated messaging and alerts, and the potential to lock out the process until the task is completed. Monitoring the task to ensure that it's been done and been done correctly. All of those different things are things that we can do to support that autonomous maintenance process. From a preventive maintenance point of view, PM has been a staple of increasing machine reliability and OEE for decades. But I don't know that I've ever talked to a company customer that is completely satisfied with, are they doing enough PMs And are they sure that they're not doing too many PMs? So on both sides of that equation, usually there's some uncertainty there in terms of, are we doing enough or are we doing too much? And are we doing the right things at all? And so being able to utilize data to look at what is the effect of the PM that's being done. Does it need to be done? Should it be done in a different way? Should it be done on a different interval? Run more, run less, et cetera. You can utilize the data from the system in order to be able to set those intervals correctly. And so certainly we can utilize data to perform studies on the effectiveness of the PM and optimize those intervals and so forth. From a condition-based maintenance point of view, this is certainly where the power of IoT starts to kick in, and most people will nod their heads and say, yeah, I get that. So if you want to put a condition-based maintenance program in place, maybe you've done an FMEA on the process and you've determined that you can mitigate or eliminate a particular failure mode if you just monitor these different variables, and when they start to trend out of control, then you perform maintenance on the machine. And those are often elements such as temperature, vibration, power draw, et cetera. And essentially, we can monitor those and just look at something simple like, is it within the range? Or you can actually kind of do an automated, why am I blanking on the term? SPC charting of that process variable, and look for the Western Electric rules of do I have different points outside of 3 sigma? Do I have 2 out of 3 points outside of 2 sigma? Do I have a certain number of points trending in the same direction, above or below the center line, et cetera? And you can utilize those rules to figure out when the process is leaving control much more rapidly. But you can do that on some of those process variables instead of just the output variable measuring the quality of the product. And then predictive maintenance is essentially the same thing as that condition-based maintenance, but we're utilizing machine learning to, first of all, determine what are the critical variables that we should be monitoring, looking at different p-values and things like that. And then also we can combine different factors together and look at how things are moving in unison. And it's really the sophistication of that model that is the primary difference between predictive and condition-based. And then predictive is just trying to look further ahead rather than saying, is the process currently out of control? Being able to utilize those same variables to predict when it will be out of control in the future. And so that's kind of the difference there, but certainly having the data is the first step in that. So that's looking at really how do we prevent the machines from going down in the first place. But no matter how well we try to do that, we still will have downtimes. And so everything up until now, it's been talking about the mean time between failure, but how do we also minimize the mean time to repair? And so if we look at the components of that time to repair, when the failure occurs, first of all, we need the operator to be aware of that. And then the operator has to do some sort of assessment to know whether it's something that they need help with, or if it's something that, it's just jammed and they can poke it with a stick. Then, if they're going to need help, they need to make maintenance or engineering aware. Someone has to be assigned to help out with that. That person has to become available if they're in the process of doing something else. They have to travel to the machine. So that's when you finally get maintenance or engineering or both, at the process itself. Then they have to diagnose the issue. They have to fix it. And then the problem is fixed. or they have to try again later. And why would they have to try again later? And by the way, what can we do using Industry 4.0 to reduce all of this? And again, I don't want to steal my thunder too much from next week, but essentially a lot of this diagnosis can be done automatically in many cases, based on the information that we collect from the machine and the fault codes and what those process variables are telling us prior to the stoppage. And if we can do that classification of that event automatically, then we can certainly automate the process of notifying the operator, notifying maintenance and engineering, giving them information about the nature of the problem so that they can assign the right person, identifying who's available and who's already on a task, and someone that has a minimum amount of travel time to the machine. And then in terms of diagnosing the issue, having that additional information available, and that kind of automatic diagnosis, and then fixing the issue, making sure that they have the right tooling, the right equipment, and everything else, that the right person is assigned to actually fix it, so that they can do all of that in a minimal amount of time. And then also, when we look at the try again later, what are the things that cause us not to fix it on the first try? And again, it could be the wrong repairman sent. This could be something as simple as it's an electrical problem and we sent a mechanical person out there to diagnose it. And so then they have to leave and the electrical person has to go out there. So being able to diagnose things and send the right repair person in the first place can help a lot. Being able to diagnose the issue on the first try, and again, if we can do that automatic classification, that certainly helps with that issue. Not having the required parts in stock. If we have that machine learning model in place and it can forecast, what are the likely failure modes, or just doing a better job with that analysis overall, we can maximize the probability that we have the parts that we're going to need in stock. Having to leave the machine to get parts from stock. This one could be as simple as having a communication mechanism in place so that the repairman doesn't have to leave the station to go to the stock room, but the parts can be delivered to that person still at the machine. Needing different tools than were brought. Again, hopefully if you can make that automatic diagnosis in many cases, they'll be able to bring the tooling that they require. If they need additional assistance, this could either be notifying multiple people at one time up front, or it could be utilizing AR technologies to get remote assistance at the machine, bringing somebody in through a phone or AR glasses or anything else to be able to assist with that. And then if they don't know how to make the repair, this could be something where, again, you have the AR library of different repairs that they can look at and then make the repair themselves. They can get that remote assistance, etc. So a lot of different ways that we can help with this using those Industry 4.0 solutions. So that's more of the maintenance focus. The next thing I want to talk about is setups and changeovers. And if we look at a SMED process and we think through the traditional kind of paper-based approach to that, a lot of that can be automated. So if we look at the task tracking itself, this could be something as straightforward as just having an easy button so that we can track, I completed that step, I completed that step, I completed that step. And we can start to analyze how long those different steps are taking. It could be something where we utilize RFID chips or something along those lines to automate the spaghetti mapping, that we do as part of a SMED process. It could be doing, video analysis of that person as they go through the process of performing that setup. So that task tracking can be automated in different ways. But we can do something as simple as comparative analysis. When Bob runs this setup, it takes an hour. When Joe runs it, it takes 3 hours. but we get much better quality parts when he does it than when Joe does it or when Bob does it. And so, if we can run that comparative analysis, find out who's doing things differently, what is the difference, why is there such a wide variance in how long it's taking, and what are the results of that, and what are the best practices, and how do we share those? Being able to kit things in advance, knowing what's next on that machine, being able to have somebody kit the parts that are going to be required for the setup, have them delivered to the line, so that as that previous job is finishing up, we have everything that we need for the setup there at the line already. And then just standard work. How do we get that defined? How do we get it documented? How do we make that available? And then how do we track deviations from that standard work as people are doing it, and then notify them of that fact? And then visual controls can also play a part in this as well, where we just have something as simple as a countdown clock, that when setup begins, that countdown clock starts going, and people see that visual feedback of what is the expected amount of time to take in order to complete the setup, and do they get it done before that amount of time? Something as simple as that countdown clock can be tremendously effective in driving commonality between the different workers and reducing variation. So when we look at process failures, I just noticed the icon that Microsoft Office chose for blocked or starved. That's interesting. So, if we're going to, if we do an analysis of the plan, and, if any of you are familiar with the goal, being able to identify the constraint within the process, and we never want to block or starve the constraint. We want to keep some amount of inventory in front of the constraint and make sure that everything after the constraint, flows smoothly, so that we don't ever, block that constraining asset. So, being able to do that analysis, being able to understand, with the different product mixes and so forth, what are the different constraints in the process, being able to manage the queues in front of that asset and after that asset are critical to maintaining that, throughput for the overall facility by maintaining the throughput of our constraining assets. Tooling issues, being able to minimize those. I'll actually show an example of this later, but if we're taking the machine down in order to replace the tooling, every X number of parts, are we taking it down unnecessarily if that tool could run longer and still produce good parts? Staffing and staffing issues. How can we effectively cross-train our people and support people that don't ordinarily run a given process if they need to step in and support that process because of absences or vacations or anything else? And then just scheduling and coordination to make sure that the right pieces are arriving at the process at the right time in order to complete the operation that's required there. Certainly, I've also been in the business of implementing, factory planning and scheduling systems and so forth. And being able to have the right data to do that is absolutely critical. I did a webinar back in January on how we ensure that we're feeding that planning system the right information, and we can minimize the gap between planned versus actuals. And then, the next really big reason for downtime in the process, or variation in the process, is manpower. And so how can we prevent those causes of variation, or at least how do we mitigate the impact of manpower on the process? And so when we look at either downtime issues or runtime issues and things like that because of the operator, are they trained properly? Are they working with out-of-date information? Do they have good quality information? Are they getting positive feedback from the process itself to let them know and make the best decisions possible? Essentially, lean. Taiichi Ono boiled it down to the process of essentially creating knowledge workers on the shop floor that can be intelligent in how they run the process. So how do we give them the information that they require, not only about their own machine, but what's happening within the greater context of the facility in order for them to make the best decisions? And then, are mistakes made due to lack of knowledge or lack of experience? Does the variability increase when new workers come on board? And is there a wide variance between the different operators that run the process, whether it's in the operation time, the amount of downtime, micro stops, setup time, et cetera? And now how do we take the best practices from our best operators and make those universal across the entire staff? And then, how do we prevent, errors? And how do we error-proof the process? I was talking with a company the other day that at their final assembly, their biggest issue with throughput was that they had I'll just say, extremely low first pass yield. And they had to do a lot of inline rework on complex machinery that they were building. And it was usually simple things. Something was painted the wrong color, or it was missing labels, or the labels were in the wrong place, or something along those lines. And so how do we error-proof the process so that we don't have to do that inline rework and so forth because of manual errors in the process earlier? And a lot of the answer to those questions is implementing standard work and making sure that everybody is trained on that standard work and has visibility to that. And then being able to detect and elevate attention to the deviations from the standards. And all of those different things can be assisted by IoT systems, by AR systems, et cetera. And certainly, expert guidance and training can help with this. So you can have one person just go through the steps in the process, kind of record what they're doing, annotate that to say, why they're doing it, what the steps are, what is required, what are the safety issues, and so forth, add each one of those steps, and be able to do that very simply and effectively by democratizing that across your work staff, instead of having one group only being able to do that. And then being able to utilize AR to really, help people visualize what's happening in that process more effectively, and being able to, utilize that to kind of error-proof the process, whether that's highlighting the bin that they're supposed to pick from, or any other assistance that we can give them to do a good job. With that, I'm going to switch over to talk about performance for just a couple minutes here. When we look at machine issues that impact performance, there's some innate variability in the process itself. And certainly, if we're monitoring, those process variables and so forth, we can identify those and, put plans in place to minimize or mitigate those. And then being able to track the micro stops as well. I've had customers that are manually collecting data kind of in parallel with the IoT automatically collecting downtime. And because of the micro stops and the short stops, we've seen results of up to actually 10 times as many downtime events being captured through that automated process as are captured manually. Because when you're capturing it manually, you typically only write it down or go to the computer to enter it. If that happens for something more than 5 minutes, more than 10 minutes, something along those lines. But we can do that automatically and track stops of 5 seconds, 10 seconds, et cetera, and how those are actually impacting the performance. Typically, those don't get bundled into the calculation for my availability of the resource, but they're just performance hits. I'm supposed to make 100 pieces per hour, but I'm only making 90. And the reason for that is that I've got these micro stops that are just slowing things down. Then from manpower issues, different operators, putting different settings into the machine, running things at different speeds, etc. Those are all the things I just talked about from a manpower perspective, fit here under performance just as well as they did under the availability section as well. Just a few examples, one of which was with a bread manufacturer, and we were collecting data from the shop floor and tagging that to what area was that issue in, what category was it, what was the cause, what product was running at the time, who was running the line, etc. And when we look at this, equipment loss was the #1 source of issues. And when we drill into that equipment loss just by clicking on that bar, and showed that oven was the biggest loss underneath the equipment loss. And when we drill into that, what we see is that most days the oven doesn't have a problem. But then occasionally we lose a huge amount of time due to the oven. And what we can see is that we're actually getting an oven shelf flipping due to a broken pin. So, as the conveyor was going through the oven, eventually those pins would fatigue and we'd have a shelf flip. And then we'd have to stop the oven, let it cool down, clean it out, fix the conveyor, reheat the oven, restart the process. And just going through that took a large amount of time when it happened. So what we were able to do is to identify what was the proper period to do the preventive maintenance of checking and replacing the pins. And by putting that PM in place, we were able to completely eliminate the biggest single source of downtime in the plant. Another example is optimizing machine part replacement and pulling information from the machine itself, vibration, noise, power consumption, other time series data, and pulling that through a partner solution of ThingWorx from PTC. We were able to create a model that looked at when the grinding wheels were getting worn, what was the pattern, and what thresholds did it have to meet in order to prevent that failure from occurring. And so we can clearly see the difference between new wheels, worn wheels, and a failed wheel. And so what we were able to do is identify where in this pattern can we set a threshold or a set of thresholds across different variables that tell us when it's time to change that wheel, so that we minimize the amount of downtime that we have for those wheel changes, as well as minimizing the cost of the wheels and the refurbishment, and also maximizing the quality that we have from the process. And then we pass that information to operators and engineers, et cetera, on computer screen, on phones, or even with AR glasses. So with that, that's the presentation for today. I'll get more in depth on some of those sections next week. And as I said, I've done a number of presentations in the past that get more depth on different topics as discussed. Please reach out to me if you like at tim@visualdecisions.com, or you can see my phone number there. And happy to discuss how to make this work within your business. Thank you very much. Bye-bye.